Hello, I'm Rob Brock and I work at KDAB. Welcome back to our mini-series about designing your first embedded Linux device. In this episode, we're going to talk about the development environment. As part of planning your embedded Linux device, you need to determine how you want to build your software. Taking the time to research your options will help you end up with a well-designed, easy-to-maintain, and cost-effective solution. In this episode, we are going to discuss which programming language to pick. We will consider what multi-platform needs you might have, discuss libraries and licensing, and finish with a brief section on developing, testing, and debugging. How do you pick which programming language to build your software with? From a 1,000-foot view, you might be constrained by some specific tool or library that is key to your product. For example, the UI framework we discussed in episode 2. You may also be constrained by hiring limitations. Will you be able to hire developers for your chosen language? If you have an existing team, what language are they proficient in? Is retraining them an option? Closer to the ground, there are many reasons to pick one language over the other. Let's look at 3 interesting choices for embedded development. The traditional route for embedded Linux products is C++. While C++ might scare people off with its infamous complexity, the C++ Standards Committee has been working hard to make the language easier and more foolproof with newer, simpler, and better programming constraints and idioms. Modern C++ is highly flexible and performant. It has been around for decades, is used widely, and has a large support community. This means that there is also large volume of third-party libraries available, allowing you to focus more on the business logic of your application. An up-and-coming alternative to C++ is Rust. Rust is also highly flexible and performant. However, unlike C++, it has been designed to guarantee memory safety and thread safety, enabling you to eliminate many classes of bugs at compile time. It has great documentation and tooling, and whilst it might not have as large an ecosystem as C++, its attractive performance, reliability, and productivity means that we are seeing more interest and uptake. Rust is also easy to integrate with other languages, so if there is some third-party library you need that isn't available for Rust, you may be able to add a Rust interface for it. Another language positioning itself into the embedded space is Dart, a programming language created by Google. The goal of Dart is to offer the most productive programming language for multi-platform development. A major selling point of the language is the ability to hot reload your code, which enables developers to quickly iterate their tasks. Dart is specialized around the needs of user interface creation and powers the Flutter UI framework. As Dart and Flutter are targeted at mobile and web app developers, you may be able to take advantage of a larger talent pool if you need to hire more developers. Not all products need multi-platform support, but unless you are developing an x86 Linux application on an x86 Linux developer machine, it's something you need to consider. The simplest case is being able to develop your product on a fast, capable developer machine, then cross-compile for testing on your low-power embedded device. On the other hand, you may have grand plans for companion mobile apps or websites. If you can write code that can be shared between these different platforms, then you save time and money. Knowing upfront what level of multi-platform support you need can help you narrow down your choice of programming language and UI framework. As we mentioned in the programming language section, you are very likely to be using third-party libraries to power your product. Before starting development on bespoke in-house solutions to a problem, it's always worthwhile checking if someone else has done it before. This is an easy way to save time and money. However, you also need to be able to build and run the third-party libraries and their dependencies on your embedded device. Depending on what the third-party library does, maintaining your application dependency chain could potentially be more effort than developing an in-house solution. Additionally, you need to consider the licensing implications of any third-party libraries that you would pull in. There are many open source licenses used by third-party libraries, and you need to make certain your product complies with their license restrictions. The final section for this video series is developing, testing, and debugging your product. This is a huge topic in itself and not something we can adequately cover in a few minutes, so we would like to draw your attention to another white paper we have published, Software Development Best Practice. This covers best practice for both desktop and embedded development, and we highly recommend you check it out via the link in the description. For now, let's briefly discuss continuous integration, or CI. When developing embedded Linux software, it is typical to build and test as much as you can on developer machines. This is simply a faster, more productive way to work. However, this makes it crucial that you have a CI setup which builds each commit for both your target architecture and your development architecture before it is submitted. This helps to ensure that you catch any breakages before they can affect the rest of the team or product. And additionally, you should build a test suite that is run on the target hardware at least nightly, if not for every submission. This allows you to iterate your product with a high degree of confidence that it actually works. In our experience, the time invested in setting up a good test suite greatly outweighs the cost of debugging broken builds during critical phases of your release cycle. Speaking of debugging, you will need to get comfortable debugging on an embedded device. Debugging on embedded hardware often has added levels of complexity to desktop debugging, from simply getting the tools you need or setting up remote debugging. We would strongly recommend setting up a crash reporting system as part of your embedded product so that when something goes wrong, you can easily access stack traces and debug logs to solve the problem. Thank you for watching this mini-series on designing your first embedded Linux device. We hope that it has highlighted a few of the things we often see overlooked in embedded Linux projects. There are links to the print version of both our white papers in the description, as well as links to our website, where you can reach out if you have any questions or need help at any point in your embedded Linux journey. If you enjoyed this series and would like more like this, let us know in the comments what you'd like to see. Goodbye.